Thank you, Koi, for inviting me here. It's my pleasure to be here. It's a little too dark, I think. Yeah. I have these different subjects, and so I gave already several talks at Komaba campus and at Hongo campus of University of Tokyo. In Hongo campus I talked about spin control in self-assembled quantum dots in Tarucha's lab, because spin is there the most important thing. Then I talked about nanowires extensively and gave an overview. And actually I will give, towards the end of next week at Komaba campus, 3 lectures in a row. In the afternoon, I think it's 1st of December, Professor Arakawa is organizing this on semiconductor hetero and nanostructures. So the first part of the lecture will be very basic, and then I go more into details. This will be next week. Here I decided to talk mainly about silicon germanium-based nanostructures, and also arsenide-based nanowires on silicon. And these are basically the topics which I will try to cover. But before I go into this, I show the people where I'm coming from. That's Munich. Actually, this is Germany in Central Europe. Here is the North Sea, here is France. Here are the Alps. Actually, Munich is in Bavaria. And Bavaria is apparently so important that I have Germany here, but Bavaria has its own name, like the other countries here. I took this just from the internet. And this is in German called München. And this is located here. And this is, for example, the Allianz Arena, where Bayern München is playing soccer or football. And in the back, when you are close, you see the Alps. It's very, probably in the back you don't see it. So this is the highest mountain in Germany here, which is the Zugspitze, which is about 1,000 meters or 800 meters lower than Mount Fuji. This is Garching. It's a small town. This is a subway connecting us to the center. So it takes about half an hour from our subway to the center of Munich. And this is a research campus in Garching. And I'm coming from this small institute, which is called Walter Schottky Institute. And this has now an expansion. So we have a new building right here, which is now called Walter Schottky institut-ZNN, Center for Nanotechnology and Nanomaterials in our neighborhood. And we have also a new building here, right in front of the subway, which is the TUM Institute for Advanced Study. And as you said, I'm so young that I'm not anymore in charge of anything. I'm a fellow of this Institute for Advanced Study, and I call myself, now I have all the freedom going 2 months to Japan, or I call myself my own postdoc. I'm my own postdoc now, so I can work again in the lab. So this is where we are working. Altogether, there may be 200 people working in the Schottky Institute and in this building in different areas. So this institute is organized by several, let's say, professors and associate professors, younger professors, covering different fields. Also these 2 buildings, and altogether maybe now roughly 200 people. Personally, I was the founder of the Schottky Institute 22 years ago, and also I initiated this new building and raised some money for this new building, which we started last year. And you were one of the first visitors in this new building. You had an office here in this first floor, so you could see what we are doing there. So these are different fields. Now, in the past, in the Schottky Institute, we paid a lot of attention to having good materials technology. And we worked on many different semiconductor materials, mostly with molecular beam epitaxy. So we have something like 7 MBE machines for the different materials, also EMO CVD. And I personally, I'm involved mainly, and this is my focus, what I call the traditional semiconductors like silicon, germanium, and gallium arsenide based 3,5. but especially for long wavelength lasers, which is a important subject. We use also indium phosphide and antimonides, and also especially in Martin Stutzmann's group, nitrides, and also diamond and other things, and graphene and carbon nanotubes nowadays, and also bioorganic materials, partly on semiconductors, but also in other structures. So I will concentrate on this, and because I did not have this in my talk before, I just added it to give you a little overview because of you. I just saw what you are doing. I gave a talk here 2.5 years ago on semiconductor quantum dots, indium arsenide, gallium arsenide. And this is based on this MBE machine, which is an ultra-high purity MBE machine, where we can grow very high mobility two-dimensional electron systems, but also this kind of self-assembled quantum dots or coupled quantum dots. So here are stacked. These are specially designed for flat surfaces by flash-off technique. And this I will concentrate a little on nanowires at the end of my talk. And just what we are doing in quantum dots is in principle always electro-optic devices with quantum dots. These are diodes with single quantum dots. This is, for example, resonantly excited. The first times that Rabi oscillations of excitons were measured in just a DC photocurrent. And this was this paper quite some time ago already, which was the first electrically measured Rabi oscillations optically excited. Then we do a lot in controlling the coupling of dots, and most of the work today is on spin control in dots, and these are more recent papers in this field. And then we do also embed dots in microcavities and do strong coupling, weak coupling, basically cavity QED effects of these dots in these areas. This is mainly John Finley. I started this kind of work, and this is now also in close collaboration with John Finley, this part of the work. So this is just to give you an overview about this field here. Now, today I will talk about these three subjects: silicon germanium heterostructures, especially double quantum dots. These are similar structures as you work on here also. Then germanium dots in photonic crystals, and 3,5 arsenide-based nanowires on silicon. Now, electrostatic quantum dots are thought to be used also for quantum information technology. And you start with a two-dimensional electron system underneath, and you make some gates and make here dots. And what you can then use is, for example, the charge left or right, the spin up or down, or singlet or triplet state is a computational basis for this. And what you need is a disorder-free two-dimensional electron gas, or at least clean, and external electrostatic confinement for quantum dots. So this is not self-assembled, not optically confined, but this is electrostatically confined. And there was a lot of work in gallium arsenide, and this is quite advanced. This is just one of the recent references in this field. Now, gallium arsenide has the problem that you have a lot of nuclear spins, and this is a source of decoherence. And then we get this thing, and then we cannot use this state basically here. So hyperfine and spin-orbit interaction dominate, and decoherence for most mature 3,5 systems, because in the 3,5 all nuclei have a nuclear spin. All isotopes have nuclear spin. So this is one of the major problems. And this was also stated, for example, in this Science article, where it was explicitly said this was one of the pioneering work for really coherent control. But that T2 times are very short in such 3,5 semiconductors. So why silicon germanium? I mean, you are working here also in this field. One is that we have very few nuclear spins. Already in natural silicon and germanium, only silicon-29 has a nuclear spin of about 5%. And in germanium, it's only the germanium-73, which has nuclear spin. And actually, this is schematics. These are about 100 atoms. And so you have 5 nuclear spins and a few silicon-30, which have no nuclear spin also in the system. But you can also grow with isotope clean materials, and you actually can also avoid cis spins or still make it lower. So there may be much longer coherence times. Now, one of our MBE machine is silicon germanium based, not just 3,5 based. And in this MBE machine, we have natural silicon as a source, silicon-28, natural germanium, germanium-73, germanium-70, and phosphorus and boron, and also manganese for magnetic, which I don't like too much in this machine because it deteriorates the mobility. But we didn't use it for quite some time now, and it's quite good what we get. So this is this MBE machine, which actually was run by Dominique Boujard. He has now a professorship in a close by university in Regensburg, and we just this summer transferred this MBE machine to Regensburg because he continues mainly with the materials part, but we still collaborate closely with physics on the systems. Now, this is a typical two-dimensional electron gas structure for silicon. Actually, we started this work on such strained layer. So this is a, what's happening now? That's a projector. That you have silicon quantum well on silicon germanium. Germanium has 4% larger lattice constant. So if you relax here the lattice constant of silicon by adding germanium, you have a so-called virtual substrate, and then you strain silicon, and actually you have then tensile strain in silicon, which splits the conduction band, and you have the lowest conduction band, minimum delta 2. This was first done in my group together with Daimler in 1984. And this is a FISREF letter which showed for the first time that in tensile strained silicon you get a splitting of these valleys and you get a strain-induced two-dimensional electron system. And still we use a very similar structure. So this is, you can then here, for example, introduce doping. We use phosphorus, other people use antimony as a donor here, and then you get an electron channel in this two-dimensional electron system. So what we have is basically a kind of a Schottky diode, so a Schottky type transistor. We put the metal on top, and then we can tune the electron systems. This is a calculation of the ground state and first excited states in such a quantum well. So we have this active modulation doped area. Now typically this is schematically shown that you have this smaller lattice constant, you bring it to a larger lattice constant, and then you have tensile strain, and this makes this band structure like this, that you have a potential well for the electrons here in the silicon. Now, this is the strain-induced quantum well, which contains the two-dimensional electron gas. So crucial for the quality is how you make this virtual substrate, because this is a graded buffer. You start with silicon and you want to have a virtual substrate with a new lattice constant, and normally you have a lot of dislocations and all kinds of problems, so this has to be optimized. And the next important thing for, let's say, single electron effects is what kind of gate are you using. And it turns out that palladium is a quite good gate, a Schottky gate for this. Actually on top we have a silicon cap, that we have basically silicon technology here. So we use the Schottky barrier of palladium on silicon to tune the electron gas. And this is the layout of such a sample. So these are the ohmic contacts with gold and some other material which go to this. In the inner part is the real sample, and these are gates. And actually this is now this inner part here, which is done by E-beam lithography, where you have here the ohmic contacts, and here you have the gate fingers, and here you define two quantum dots on top here, and you have a charge sensor, for example, here, which can measure the charge in a dot, for example. So we have this edged meso. This is this inner part here. This part is the edged meso. And then we have ohmic contacts outside. We have the gate electrodes. And then we have the quantum dot. And we have this sensor also on this side. And we can measure, for example, source drain current through this dot. And have here gates on each side to control the charging in the dot. Now typically this is more tutorial. but this is real the data from such a device on silicon. So this is what do we do when we sense such a dot. So we have these are the Coulomb blockade peaks when we have, let's say, some voltage on the right bias, and we measure, for example, this sensor here. And this Coulomb blockade peak we use like this, that when we are on top, we have a lot of current through. When we are in between here, we have no current, it's blocked. And when it's just starting, very few electrons can go over. We have an intermediate current. And here on this slope, this is very sensitive for charge. If I add now here a charge, this will be sensitive seen by this, let's say, point contact here. And that's what we are using. And actually, this is now, with respect to the left gate here, that we change the left gate in a certain range, and we measure the change in the current through this point contact when we maybe sit on this slope here, and then you see each extra electron coming into the dot by this change in the sensor here. Now with this you can do, let's say, a two-dimensional mapping. So this is the right gate here, and this is the left gate here. This scale, and then you have this stability diagram, and actually just also more tutorial how this works. If I am in this situation here, for example, a certain number of electrons in the left and right dot, so this is the left and the right dot here, then I am here in this regime. I have an occupation of Nm. So when I change the bias, then I can tunnel in an electron from this side here. Then I move over into this regime. I have now one electron more on the right dot. If I change the bias like this, then I move this electron over to the left dot, and then I move in this direction. And if I, let's say, have the bias like this, I add another electron, and then I move into this. So this is how this single charge control and sensing works. So this is tutorial, but it's also real measured in this silicon germanium device. This is the measurement, so it's a delta I sensor. This color code is changing from here to here. We go from the red to the yellow region. We change the current stepwise when we add an electron into the system here. However, in silicon germanium, it's quite difficult to reach the single electron limit due to the relatively large effective mass compared to gallium arsenide, for example. That's why we were not able to really get with this device to the single electron limit. So more recently, we have made new devices with different e-beam, let's say, parameters, which have much narrower lines, and altogether the size is shrinked, and they can control the tunneling barrier better here. And with this, we can now really go to the single electron limit in the case of silicon. And the other thing what we can do is we can go to nuclear spin-free system. So we can just grow the active layer with silicon-28, and then we have negligible nuclear spins, and also the surrounding we can grow with germanium-70 instead of 73, and then we have no nuclear spins in the system, and then we expect even longer, let's say, decoherence times in silicon. This MBE machine has a silicon-28 source in here. It's a small e-beam evaporator, and has a germanium source as an evaporation, as a Knudsen cell, germanium-70 and 73 separate here. And so what we then grow is this part isotope clean, the rest with natural silicon, don't use all this valuable isotope clean material where we don't have so much material. So we grow only this part isotope clean but nuclear spin free. And actually this worked already quite some time ago. 2 years ago we had already such material, but it was very difficult to really control it. So this is, let's say, a heterostructure with purified source material. This is a SIMS measurement. What we get, this is this germanium, this silicon quantum well. And you see that we have here, this is a germanium. This is a silicon quantum well here. So here we have the silicon-28, a little higher, and reduction in silicon 29 and 30. And this is the kind of purity we get in such systems. So this is a logarithmic scale here, so it's a few orders of magnitude which we reduce, especially the silicon 28 is the important thing. And actually, in the moment, we have the best sample of isotope clean material with a mobility of 55,000, which is comparable to what you have with natural silicon. We were a little concerned if we really get high enough mobility, so Shubnikov-de Haas oscillations start at about 0.5 Tesla, which gives you this kind of mobility in silicon 28. And so this is actually one of the structures. This is the isotope clean part here. This is a silicon channel. And we could not adjust the concentration perfectly from the natural to the isotope clean because we use these different sources. And so we had to have different germanium concentration here than in the relaxed buffer layer. But nevertheless, we get quite high mobility. And the mean free path is then more than 350. We have made these devices, and in the moment they are in the cryostat. This was a pre-measurement at 330 millikelvin, gate voltage left and right here. So this is just measuring the charging with one gate voltage and source drain currents through here. And in the moment we have transferred this sample to the dilution fridge in Stefan Ludwig's lab in the Ludwig-Maximilians University in Munich. And there are very nice results already coming out now for this isotope clean material. And it looks very stable from the gating. Now this part of the work is done in collaboration also with here. The isotope clean material, and we have a lot of discussions, and we work in the dilution fridge in the moment at LMU, and we have funding. These are the most important funding which we have through all the projects. Then we have more detailed fundings also for this special project. So this was the first part. Any question to this part? Maybe we can discuss afterwards, but I mean, okay, because then I come to the next, which is germanium dots in photonic crystal environments. Now again, I stay with the silicon germanium system. And now it depends how you change the growth conditions. Before I said you have to get a relaxed buffer to get this drained channel. So you can do this under certain growth conditions that the relaxation occurs via misfit dislocations. If you change the growth conditions, and especially if you have a high germanium concentration, then you form islands. And this depends on the growth temperature typically and other parameters, but mainly growth temperature. If you get these very small hot clusters, which have a height of 1 to 2 nanometers, if you get these pyramids, or a mixture between pyramids, and in literature these things are called domes, which have different facets here, but you can have quite pure only pyramids, or a high density of these domes in such a system. So this is a scale 500 nanometer. And if you go to silicon germanium, so you don't go to pure germanium, you can also grow very large and rather flat islands. Here the scale is changed. So each island has maybe 100 nanometer, let's say, length here and width, and the height is 4 to 8 nanometers. This may have an advantage compared to these dots for optical properties, because these dots, high germanium in silicon, has typically type 2 band offset, which means the electrons are in the surrounding silicon, the holes in the germanium, so it's spatially indirect, while this has type 1 band offset. So you get the electrons also into these islands and have more spatial overlap, and in optics you win due to the excitonic effect in oscillator strengths. So we are in the moment trying to work with this, but most of the work is done with this more pyramids or domes. Now if you look at the luminescence of such pyramids and domes, you see this bimodal behavior a little, but very broad, inhomogeneous broadened because of different size. Actually this was also done quite some time ago, nearly at the same time. This is Shiraki's group here in Tokyo, and this is my group. And we have exactly the same paper. We didn't know of each other. There is, let's say, the spectra look very similar for the first germanium dots, only we plotted increasing germanium contents from top down and they plotted it bottom up. That's the only difference in a way. And this is the luminescence of these large islands. So this is very new now. And here you see much nicer, like the silicon, so TO, the no phonon line and a TO replica. Those who are familiar with silicon luminescence. And we believe that these lines may be better usable than these lines for photonic crystal. But nevertheless, we try to make efficient light emission out of germanium, even though it's indirect in real space and K-space, by redistribution of the emitted light, by bringing it in a different photonic environment, and by shortening of radiative lifetime by the so-called Purcell effect. And one of the membranes which we make as photonic crystals, it's two-dimensional, is basically a silicon on insulator. We have silicon substrate, silicon dioxide, and then silicon actually epitaxial grown within the top silicon layer down to something like 20 to 30 nanometers, and then grow with MBE and have an active layer in here. And if I want to see what the dots are, I can also have one on the top under similar growth conditions. But for the active samples, we use only this sample in between. And then we can fabricate with E-beam lithography holes into such a membrane, under etch the silicon dioxide, and then you have a two-dimensional photonic crystal here. And you can also make a resonator, this defect, which shifts the holes light, and then you get modes. So what you get in such a crystal is this is a two-dimensional photonic crystal, so it's a periodic variation of air and silicon. So these are just holes punched through this silicon membrane, so it's freestanding membrane. And if you look at the photonic properties of this, so this is a light cone, so the dispersion of photons is linear, and then due to this periodic structure, we get here this photonic band gap. So here, no photons can be, let's say, emitted in this direction, in this field. So what happens if I have a quantum dot which normally emits light in all directions? In such a photonic crystal, I can redirect the light in one direction. Actually, when I have these defects, and depending on the defect, we have in this photonic band gap also cavity modes. This is like a defect in a semiconductor. If you have a donor in a semiconductor, it gives you a level in the band gap, and this is in the photonic crystal. It's also I have a band structure for photons, and I have a defect here, and this gives me just states in the band gap. And in this case, in this kind of cavity, which is often called L3 cavity because 3 holes are missing here, we get these 6 cavity modes in the system. Now, what do you see in the luminescence? This is a logarithmic scale of the luminescence of germanium islands. Here you see the silicon, let's say, lines. This is TO phonon replica. This is 2 TO phonons. This is TA, which is well known in silicon luminescence. And these are the germanium islands here. This is measured outside. Now, when I just go onto the photonic crystal, I see already an enhancement of the emission by maybe a factor of 10. And then when I go into this cavity here, into this defect here, then I see this cavity modes which have different widths here. So this is one, this may be overlapping several ones, and this is one of these modes, and this is the end of the photonic band gap here. And you see, in these modes, we get an enhancement of the luminescence maybe by a factor of 100, depending where you are. And this is mainly redistribution of the light, outcoupling, but it's also Purcell effect if the cavity is good enough here. Now, we did a very detailed study of this cavity effect. So what we tried to analyze is, so this is just these modes on a background. Because this is a small scale, so you don't see this broad background anymore. And these are the modes when we change, for example, the radius of these holes and keep, for example, the lattice constant A the same. This is what we measure with microPL outside, a very broad and weak luminescence with 50 millielectron volts, and this what we measure inside this cavity, we get these modes. So what we tried in a certain spectral range to look at the intensity of these modes depending on what Q factor I have in this mode. And then for the optics people, first of all, it looks surprising, but if you do think a little, it may be okay. If you plot now the intensity, you see the M1 mode has the highest Q factor. It's the narrowest mode, and all are in the same spectral range that we can compare the intensity because we changed the cavity like this. So the M1 mode has the highest Q, so here's 1 over Q. So this is already something like 6,000-7,000 here, so Q or 5,000. And you see the intensity is, however, lowest. If the Q is not so good, we plotted here the integrated intensity over the mode, you get higher intensity. And this has to do that we couple, let's say, if I couple a high Q cavity to an oscillator which has a lower Q, then you get most of the intensity when the Q is not so good and it overlaps with the oscillator cavity. So it's if you want to just get light out, too high Q is finally going down in intensity. And we did a detailed theory, and also when you change the excitation power, you see a dependence. This is due to free carrier excitation and free carrier absorption.
How many dots are you coupling to the cavity?
We believe that we couple roughly 100 dots to the cavity in this regime here. It's not a single dot. And then you average, and depends on the detuning also, because you couple also if you're not exactly tuned because of the broader width of the oscillator. And that's why the intensity, the total intensity, even though it's a very narrow line, goes down when Q is improving. This is the reason. So when you want to make in silicon an efficient light source, Q should be not too high when you use this as an emitter. Some of you may know Norman Hauke. He was also involved in the other work. He was here together with Thomas Zabel in the beginning of this year until the big earthquake. Then they came back, but he came later again. And together with a group of Arakawa, we started using the same germanium islands now and embed them in three-dimensional photonic crystals. And this is a very interesting technique, which I think only Anivat Nurat can really do this in a special SEM electron microscope. So what we did, we prepared in Munich all these platelets. So all is MBE grown, so passive layers and the active layers. And we did electron beam lithography. We have exactly the same E-beam writing system as in Arakawa's lab. And we just used the parameters they used. And then he came with a lot of these platelets. And then Anivat stacked them on top of each other. So this is a stacking of platelets which have just lines. And then when you then have the lowest lines in one direction, the next one in the opposite, and then you rotate, you get actually here an electron micrograph of this structure from the top. And you see, let's say, this period of 4 of the different lines. So here it's color coded, and here you see it. What is the top line is this, the next line is this one, and the third line is this one, and the fourth line is this one underneath. And this is one period, and this goes with an accuracy of 50 nanometer. So this is now we stack this on top of each other, but then we also introduced a defect. So in the center we have placed one plate which has these germanium islands and has in the middle no lines. So it's in 3 dimensions now, a photonic crystal cavity. And this, compared to the 2-dimensional photonic crystal, has now a complete photonic band gap in all 3 directions. And so this is just a simulation for this geometry, for this crystal structure which we have. It's a three-dimensional photonic crystal, like you build up an electronic crystal from semiconductors by arranging atoms. We arrange now this, let's say, photonic band gap periodically with a unit cell of 4 in this direction. Here, 4 such platelets. And then we get this complete photonic band gap.
So this is the FCC crystal?
In principle, yes, yeah.
Because you have the...
Right. Now, when you look at the spectrum of the germanium islands, this is again the germanium islands of this one thin plate outside. And I expanded this here by a factor of 20. And now you measure on this photonic crystal, you see immediately that you get, again, with these very sharp lines, which are modes in the system. And actually, we believe that the 2 strongest modes are these modes from simulation. They are in the plane the same, but out of the planes they have a different pattern. And this is this mode A and B, which is strongest in this photonic crystal. So we have here a factor of 30 and 58 enhancement compared to the unpatterned, and these 2 modes are very strongly polarized here. And actually the polarization is 95%, while this random luminescence is not polarized, so as reference. Now when you plot this, now in this photonic crystal we could go down much lower in excitation, so we have a very low excitation power of less than a microwatt here. And what we see is these are the modes A and B here at 1 microwatt, at 10 microwatt excitation and 100 microwatt. You see Q is not changing. And the intensity is in the beginning going linear, and then it's more like 2/3, which indicates that we have here indeed radiative recombination, and here maybe Auger effects or non-radiative recombination plays a role, and then you go away from the slope roughly 1 here. Actually, if you look at the Q factor in this 3-dimensional photonic crystal, this is a logarithmic, semi-logarithmic scale here. So the mode is coming up, and also what you learn in classes that you need at least 1 unit cell to start. Let's say this is exactly what we have. We need here something like 4, 5 top layers. This is the number of top plates, and then we measure. So when we have no top plate, we don't measure any mode. We have only the stack below, and then we add 1 plate after the other and measure the luminescence, and then you see how these modes are coming up, and then these are very strong here, and then they are decaying again in intensity because light is not coming out anymore. Because if I have more plates on top, I confine the light inside, and the light cannot be extracted anymore. But if you look at the Q factors, these last modes here have the highest Q factor. So the Q factor is just increasing up to more than 10,000 here. And this is close that you can also have in this system strong coupling. If we would have a good emitter, germanium is not a good emitter. We thought maybe bismuth is a good emitter in this cavity. But so this is the highest Q measured so far in such 3-dimensional photonic crystals in silicon. And actually, this is for the first time also that we think we have evidence already for Purcell effect. If we do the time, let's say, dependent measurement, we get the shortening of the lifetime also by a factor of 3 from the mode to the reference sample, just the platelet with the defect cavity. So this work is done mainly by Norman Hauke together with Anivat, and Thomas Zabel did the MBE growth of these platelets. And these are the people involved in this work on photonic crystals with germanium dots and islands. And we do this in collaboration with the group of Professor Akawa, where I'm in the moment also a guest professor at the University of Tokyo. Okay, this was the second part. And now in the last part, I again stick to silicon, but not completely. We use a different MBE machine. It's not the silicon-based MBE machine, but it's the gallium arsenide based. Now, nanowires. Now you see here an example of a nanowire with a droplet. Nanowires are grown normally with an external catalyst. People are using gold, and this is an old story. I mean, the first growth of silicon with gold was in the end of the 50s by Wagner and Ellis. Actually, it's interesting, their paper was not cited too often, over 40 years. And since now 10 years, it's cited 400 to 500 times per year. So it has now, in the last 10 years, got more than 3,000 citations because they sort of had the first paper on vapor liquid solid growth, how it's called. So what people do normally is they have a droplet of gold, then you put in silicon in any form, can be also from more chemistry side, and then you get the saturation of this liquid, so at a certain temperature. And if you are super saturated, you start nucleating the silicon, and then the wire grows, and the droplet is just shifted up. So it acts as a catalyst. That's why one says gold is a catalyst for this growth. It's not incorporated apart from what under this temperature and conditions you incorporate as impurity. Now gold is, however, a deep level in semiconductors, and therefore often not compatible with many things. That's especially silicon. People don't like gold at all. In 3.5 it's not so important. So what we tried a few years ago, if we can replace the gold by gallium. And so we used again our ultra high purity MBE machine. So this is a 3.5 MBE machine where we have as source arsenic, gallium, indium, aluminium. And as dopant we have silicon and carbon. So for N and P type dopant. And so we said I don't want to have gold in this machine because it's an ultra high purity MBE machine where we have very high mobility. So can we do this with gallium, for example? So instead of gold, we use gallium, and then we gather arsenic 4, but then we use this droplet also for growth. So we have to, gold would just go up, be lifted upwards. The gallium is used as a material for growing the gallium arsenide, so we have to open also the gallium shutter and provide enough gallium to have it stable. Now this is an example of such a gallium arsenide nanowire where we used a little too much gallium, so the gallium droplet is growing. And that's why it's inverse tapered. If you have a little too less, then it's tapered in the opposite direction. And if you adjust it correctly, then you get very straight gallium arsenide nanowires. And this is, let's say, and what we can do now is, because this has a very small footprint, we can, instead of gallium arsenide, also use now silicon as a substrate. So it works on silicon, and we can also grow indium arsenide on silicon, even with this large difference in the lattice constant. Let's say on gallium arsenide, we need a thin silicon dioxide, because otherwise gallium is more wetting the surface but not making droplets. And this is so thin that we then have pinholes where we nucleate the gallium and then we get the wires. And these were our first results about 3 or 4 years ago on gallium arsenide. And you see immediately that we have epitaxial relation. They grow along the 111B direction. When I take a 001 substrate, they are tilted because they want to grow in a different direction. They have a hexagonal shape here, which is formed by 110 facets. And for gallium arsenide, we have a limited growth rate, as a certain temperature where we can grow this. So they grow vertical here. So this, I think, was the very first samples which we have grown about 4 years ago now. The same growth principle works also for indium arsenide and also on silicon. So this is this thin oxide on silicon 110. So what we do is, now this is a bare surface with natural oxides, then we sputter then we do an HF etching and get these pinholes in the system, and in these pinholes we then get the growth of these nanowires, and also they have this same shape. So this is just on silicon random growth. However, for indium arsenide, this is for materials people, we need a lower temperature. Instead of 600, we need 500 centigrade, about 100 lower. But actually, in indium arsenide, we have a relatively broad range. It depends now on the arsenic pressure, and this is the axial nanowire growth rate depending on temperature and some parameters. So it's determined mainly by the arsenic flux, and we have a wide range for these indium arsenide nanowires. So if you look now careful how this changes, you see there are certain temperature range where you can get much cleaner nanowires, and others where you have a lot of growth on the surface and very few nanowires. So this is a systematic study of this. This belongs to this red thing here, and these are from this blue curve, just some examples. Now, indium arsenide is now not vapor liquid solid growth. So for materials people, this is quite surprising. There are people who claim you cannot grow wires without vapor liquid solid growth. I think this is vapor solid growth. We have several, let's say, evidence for this. First of all, we never see a droplet, but this can be evaporated before you really measure it. So this is not the proof. But when we do in situ read, what we see is that we have immediately after we open the indium shutter, we have already a relaxation of the lattice constant and a change, and so we have no delay. When we do this with gallium arsenide, with the gallium droplet, we have here a delay because we have to form first the gallium droplet. And for indium arsenide, it starts immediately after you open the indium shutter, you get the growth. And we have also other detailed analysis of this. Now, the question is, can we do this also patterns? This is important for maybe applications in future. And we bring also in the moment, let's say, quantum dots inside these nanowires by changing the composition. Now, we just used, let's say, a silicon substrate with 20 nanometer good oxide. It's a thermal oxide. And then we pattern it, and we have then these holes. This is these holes here in regular distance. So the flatness is very good. It's 0.2 nanometers of this oxide. And this is a hole shown enlarged. This is an 80 nanometer hole. We changed the pitch in a wide range and changed the diameter in a wide range. And looked what we get. And actually, again, you see there's a certain temperature where this is optimum, in this case 480 centigrade on such pattern substrate, and then you can get highly regular arrays with a yield which is more than 95% for indium arsenide. This is now indium arsenide on silicon. This is the edge of one of these patterned fields, so there is nothing outside. However, the wires at the outside are slightly larger, and that's because they can collect more material from diffusion from the outside than inside, because this is limited by the pitch distance. If you change the pitch, make them further apart, then you can also get very homogeneous height in this system. So these are some examples, growth parameters. So we can grow thick or very thin. The thinnest nanowires we have grown in the moment are 20 nanometers in diameter. We can do this also for gallium arsenide on silicon. The yield is not so high. So this is just a parameter like the arsenic flux. These are arsenide, gallium arsenide wires on silicon. In this case on unpatterned, just random holes. But we can also switch here from the vapor liquid solid growth with the droplet to non-vapor liquid solid if we increase the arsenic flux. If the arsenic flux is high enough, then we get, let's say, not this gallium droplet, and we start immediately with the growth of these wires. And this again, you see, if you have this catalyst-free non-VLS growth, then you get facets at the end, and if you have the VLS growth, you get the droplet. And these nanowires, if they are grown in this mode, are over a long part single crystalline zinc blend in this case, and they have some defects at the beginning and at the end when we cool down this. And at the moment we are doing embed here quantum dots in such a system, and we do a lot of optics and also transport in these nanowires. Actually, this is not the same scale because I didn't have the same kind of figures. This is again comparing indium arsenide on silicon and gallium arsenide. You see the yield is not as good. This is a patterned silicon substrate here. Here are no holes outside, but we can also get rid of all these clusters which we normally have on such a surface. We have them in here. They nucleate partly also in the holes. And the yield here is only something like 50% of wires. So in the moment we are still working with the growth conditions to get a high yield, because what finally one of the goals is not working maybe with single wires, but making them on silicon. They are in the hole. You have maybe a doped silicon substrate. This is a back contact. Then you have the nanowire. Indium arsenide is N-type. So if you then have a top electrode here, depending if you use P-type substrate, you have immediately a PN junction for many of these wires. We can also grow coaxial structures. We can overgrow them with the other doping or with heterostructures, with aluminium gallium arsenide, and we can embed quantum dots in such a system. But this was, let's say, I talked about this 2 weeks ago at Komaba campus extensively about these nanowires and electrical and optical properties. Here I just wanted to add it because it fits a little into my subject today, silicon, because we grow now these 3,5 nanowires on silicon, basically defect-free. So we can combine 3,5 with silicon, and also we can change doping and heterostructures. Despite of the large lattice mismatch, because they are so narrow, these wires. At the moment we are testing if we can go to indium gallium arsenide, which is very important for axial heterostructures. This is just the first trial that we have here, 19%, let's say in this case gallium, because we start with indium arsenide here. And we do the same thing from the gallium arsenide side. And we have first successful wires also and first heterostructures along the wire. Just the optical properties, the indium arsenide nanowires, this is an ensemble measurement maybe of 8 to 25 nanowires. This is in the mid-infrared. It's at 0.4 electron volts. They all show luminescence. We get the blue shift, which we believe, however, is due to structure of this indium arsenide nanowires. And in gallium arsenide, you see this is a relatively thin nanowires. This doesn't show a lot of luminescence at the gallium arsenide gap, basically. But if we cap it a little with aluminium gallium arsenide, protect the surface, we get the immediate effect of 1,000 more intensity. And a very thin cap is already sufficient. So this is bare gallium arsenide, and this is actually averaged over 15 different wires from the same growth. So this error bar is the statistical variation in the intensity.
Is it broader?
Pardon?
Why is the black curve broader?
Let's say this is this example which I show here. The width depends on the structure of the initial part, and this was a different wafer where we later found that this wire has higher density of twin dislocations, which gives you altogether a broader line. But this doesn't, let's say, despite of this, we got, let's say, a strong increase in the intensity. We have now much cleaner wires which show a similar behavior, but let's say the message is, if you saturate the surface states by making a heterostructure around aluminium gallium arsenide and a thin gallium arsenide cap, the excitons cannot have non-radiative recombination at the surface, and then you get this factor thousands of increase in intensity, and it doesn't really matter, let's say, a very thin layer is already sufficient for this. Actually, this is the thickest shell, and we can grow this as thick for optics people again, that we can have wave guiding along the wire, because the core has a higher refractive index than the shell, so we get a wave guiding along these wires. So this work on these nanowires on silicon is done by these people here. Gregor Kobelmüller is responsible for this MBE together with Max Pichler, a very important technician. These are the two people who optimize this growth and study this materials work, and these are the people who do more the spectroscopy, the transport, the structural characterization, and we are also working in thermoelectrics with such wires. So we have different areas of research, which, and I said this last 2 weeks ago, I'm quite proud that I have 4 women next to 4 men, which is very rare in physics in this group here. With this, I show you again, let's say, the research area. The new buildings are not yet on this photo, and I thank you for your attention. Thank you.